This video is going to cover some of the basics about how programs are actually structured and built and how we can kind of conceptualize how to approach the computational logic that's necessary to write a program. So to do this, we're going to spend some time talking about something called flow control or control flow. And specifically, we're going to talk about the way that we control the flow of code by using conditional statements such as if and else's, and also for other entities like for loops. So, what is flow control or control flow? At its heart, it's basically just an order of operations. It's the logic of the program. It's the order in which things occur, right? And what these do is they actually set up the axioms or the rules by which we believe that whatever code we write is going to work. And when it does this, we sort of create what's known as a computational logic. And this, it's when we say logic, you automatically might think of mathematics and philosophy, right? So this process of computational logic actually has its origins in human knowledge systems, specifically in mathematical notation. So we also get, because of that, is we get a lot of overlap between how computational logic works and mathematical logic works. Computational logic is made up of both logic programming, so sets of sentences in logical form that express facts and rules about some sort of problem, but also Boolean logic, right? And this is an idea where we might have a bunch of circuits and switches that are turned on and off based upon some sort of conditional framework. What are conditionals? Conditionals are statements where different computations or actions depend on whether a programmer has specified a Boolean condition to be true or false. So there's some sort of if something is true, then do this, or do some other thing, else do some other thing. And so this is a classic way to think about how programs are structured. So we could take a case here where we might have some condition. If it's true, then we're going to do something here, and then the program will end. Else, if some other condition is true, then it's going to do a second thing. Or if neither of those two are true, then it'll do some other outcome, right? And so based upon these true-false statement evaluations, we can figure out whether or not what the outcome is going to be and how our program might progress. All of this is related to the idea of algorithm. And algorithms are things that are around us all the time. It sounds like a fancy word, right? They're basically self-contained steps for a series of operations to solve a problem. And what makes this particularly interesting is that algorithms are things that we use every day and all the time. So you probably use an algorithm when you wake up in the morning. You'll wake up in the morning, you'll take a shower, maybe you'll work out before you take a shower, and then you'll make your coffee, you'll have some breakfast, you'll search your phone, like whatever it is that's like your normal routine. That routine is something that you've established to, say, accomplish the goal of starting your day or working out or waking you up, some sort of process, and it's a step-by-step process. That's basically an algorithm, right? It's something you can repeat day after day, and it accomplishes a specific task. Now, we use algorithms all the time. Every time you do a Google search, you use an algorithm. Every time you pick something on Netflix or you get a suggestion on Netflix, you're participating or using an algorithm. Every time you type something in your phone and it gives you a suggestion on the spelling of a word or what the next word you want to write is, that's also an algorithm, right? And so this is how we build code and programs, is that we build up these algorithms, these rules, and then we write code to execute those rules. So how do we get to that part of like, well, I've got this problem, I want to write code for it? It's kind of feels like a big jump. Well, one of the things that I think that is often not appreciated in programming, especially when you're starting off learning and you just want to pick up like all the words, all the syntax, you want to accomplish specific tasks, is sort of the thought process that goes behind like how we actually code. And to do that and do it well, learning how to do pseudocoding or how to generate a flowchart is a really important step. When I say pseudocode, basically what I'm talking about is like an informal way of describing how a program or algorithm works. And the reason why you do this is if you can write it out in this sort of non-standardized format, then what ends up happening is you kind of are able to think about, what are the steps I need you to do to improve my code? How does it need to be structured? And hopefully you end up with a simpler, faster bit of code. Just a heads up on what some of the symbols we're going to be looking at and some of the diagrams coming up. Arrows just sort of point you to what you are to execute next. Rectangles are statements. Diamonds make decisions. Parallelograms are for input and output, and the ovals are the start and the end of the program. So if we think about this in terms of a simple if statement, we have our start of the program. We might input in some information, and then we say if some condition is true, right? If some condition is true, then we're going to do something and output some other information, right? And if it's not true, then we'll just skip these commands and we'll just go right to the end. Now, say there's more than one condition that you want to meet. So the conditions here are, if it's true, I want to do the same process, right? But if it's false, I'd rather do a different process. Not no process at all, but a different process. So if it's this kind of case, then we could think of just using this if-else statement structure. Now, if we think about loops, we might diagram them in a different way, right? If we think about a for loop, you might have seen this before. Remember this one before, but we input some information, and then we're going to loop as many times as there are items in the list. And every time that looping variable is going to change to the value of that previous list. So if we had to do something to the sizes of 5 different individuals, right, we would take that data and then we could look at what the output was from each of those items in that list. We also have other kinds of loops that we might use. There's the while loop, and this basically says, like, instead of doing looping as many times as there are items in that list, I'm just going to loop as many times until this condition becomes false. So I set some kind of condition, and it's just going to keep going on until the condition becomes false, and then it'll stop the loop. So these are some of the standard ways we might think about diagramming code. We're going to spend some time in class both diagramming code and talking about pseudocode and our ways to approach it and use it as a useful tool in learning how to code. So thank you for your time.